This is going to be a pretty brief video. I know how much you guys love those 40-minute ones, but we're going to make this one as short as possible. We're going to be going over what's called SI, there we go, SI units. Now SI units are what we call, it's actually called the International System of Units. Okay, why is it SI? Because in France they call it Système International, obviously with my poor French accent. And what they are is just some agreed upon units, because if they didn't have agreed upon units, then maybe one country would use feet, one would use meter, somebody else would use spans or something like that, or a cubit. I think that was back in the Roman days, so probably nobody would use that. But there'd be all different types of measurement used, and we take all of science just interpreting and converting units, and be a lot better if we can all just agree on the units we're going to use. So they came up with these 7 base units. They call them base units because by multiplying these by each other and squaring them and cubing them and things like that, we come up with all the other units. Here are the 7 base units. Meters, which measures length. Kilograms, which measures mass. I know that's kind of weird. You would think it would be grams, but it isn't. It's kilograms. Kelvin measures temperature. Okay, it's not Celsius and it's not Fahrenheit. Obviously, we knew it wasn't Fahrenheit, but it's also not Celsius. It's a newer, probably the newest measurement for temperature, which is called Kelvin. We'll tell you about that in a moment. Seconds measure time. Moles measure amount. I know you're saying, what on earth is a mole? Don't worry about it right now. We'll talk about it later, but it's a really, really big number to measure an amount, and there's a good reason for it, but we'll tell you that. Okay, now there are also some other non-SI units that still hang around. Some of them that you'll see are things like calorie, and you'll also see some derived units. Derived units are units that are based on those basic units we just saw. There's some combination of basic units. And for example, just because we use calorie, another one is joules. And joules is kilograms, meters squared per seconds squared. As you can see, even though you just use the term joules, it's made up of all of these base units. All right. Do you need to worry about this right now? No, don't worry about it. Okay, don't focus on it. My only point in showing you that is to show you what a derived unit is. The derived unit is based on the basic units or the base units, and when you square them, when you divide them by each other or multiply them by each other, or the combination of all 3, you'll come up with other units. So that's just so you're aware that even though we're only showing you 5 units, and by the way, I forgot to mention that the only reason we showed you just 5 units, even though we mentioned 7 units, is because the other 2 are not so common for chemistry. Okay, they are amperes and also candelas, and those are just ones that we just really don't use that much, and so we're not going to throw them in the mix. But these ones you do want to learn and to remember, okay? And even though a couple of them, even though mole we'll just be talking about in a chapter or 2, you do want to make sure that these ones you understand what they are and what they measure. All right, so then we have these units of measurement, and then we want to be able to measure things that are not just a meter in length, but they might be millions of meters in length. And if we only use meters, then we would have humongous numbers and tiny numbers. And so we come up with prefixes that essentially mean millions of meters, or 1,000 meters, or 1/1000th of a meter. And these are, okay, we'll skip that. Okay, these are those prefixes. Okay, so you can see them right here. You've got, I don't know why we have the writing on here, so you'll have to ignore that. You will want to remember every one of these, okay, and remember what they mean. If you have a mega meter, which we really don't hear about much, but if we had a mega meter, that would mean we have 1 million meters. A kilometer, kilo means 1,000. So a kilometer means 1,000 meters. Of course, decimeter, centimeter, millimeter is a common one. Millimeter means 1/1000th, or 1,000th of a meter. Okay, so in other words, there's 1,000 millimeters in a meter. And then we have a micrometer, is a little bit less common. It's 1/1,000,000th of a meter. Now, micrometers and nanometers are very important in chemistry because chemistry involves oftentimes very small objects or atoms that we're measuring. And when we get down to these nanometer sizes, that's when we start to talk about the diameter of an atom, okay? It would be measured in nanometers. Okay, so a nanometer is 1/1000th of a meter, okay? So 1/1000th of a meter, all right? So it's going to be 0.00000, so it's 0 point, then 8 zeros, and then 1 would be a nanometer, all right? And then a picometer is 10 to the negative 12th, all right? So that's going to be 11, or 0, then a decimal, 11 zeros, and then a 1 would be a picometer. All right, we're going to put these on Quizlet so you can learn them. A couple of other concepts we want to cover related to these SI units. Okay, first we want to talk about mass versus weight. Okay, these are, when we talk about common conversation, these terms are essentially interchangeable. Okay, but in chemistry, in physics, in science in general, they have very different meanings. Okay, mass is the amount of matter something contains. Weight is the force that gravity pulls on an object. So the force with which gravity pulls on an object. Here's the key. Mass is the same no matter where you are. That's the key. If you're on Earth or on the moon, the mass will be the same. All right. Weight, on the other hand, will change depending on how much gravity is exerted by that planet, okay, or by whatever object is creating the gravity. Okay. Secondly, we're going to skip that. Kilogram versus gram. We already know that gram is 1,000 grams. And then to measure mass, you use the triple beam balance. Essentially, a triple beam balance is very similar to the old scale that you see, kind of like the one that you see on a courthouse that would have something over here and something over here. So you'd put your object in here, okay? We'll say you've got a little box, and then over here you put little masses that you know exactly what their mass is, and then once they balance out, then that would determine what the mass of this is, okay? Interestingly, if you took one of these types of scales to another planet, the mass would measure exactly the same. And you can imagine why that's the case, because any reduction in force on this object will also result in a reduction in force on this object, so their relative balance would stay the same, essentially. And that's essentially how this works, this triple beam balance, which is what we'll be using in chemistry. And then one other concept, which is a very important concept, is temperature. Temperature is a measure. Okay, here it says how hot or cold an object is. Actually, it's a little different than that. It's actually the measure of how rapidly each of the little molecules are moving. The more rapidly they're moving, the higher the temperature. Okay, that's why something is experienced as hot and cold. We'll go into that a lot more later, but what's important at this point is we want to talk about two different scales, the Celsius scale and the Kelvin scale. Don't worry who they're named after, okay? These guys will get enough credit in history. We don't have to worry about it in our class, all right? But you do need to understand the difference between these scales. And I kind of want you to understand why Kelvin exists. You know, why weren't we just satisfied with Celsius? There's some good reasons for it. Let me show you this one. Okay, this might look confusing at first, but what it is it is a comparison between the three scales that are familiar to us. Okay, here's the Fahrenheit scale. Try that again. Here's the Fahrenheit scale. Here's the Celsius scale. Those are the two that most of us understand. Here's some interesting facts. Okay, we know that water boils at 212 degrees Fahrenheit. In Celsius, it's much more nice and round. It's 100 degrees Celsius. Then water freezes at 32 degrees Fahrenheit, and it freezes at 0 degrees Celsius. Okay, it's good to know that. In fact, that's how the Celsius scale was originally, how it originally came to be. Is somebody found out what temperature water froze at, and then they found out what temperature water boils at, and they divided that difference into 100 increments. And that's how we came up with the Celsius scale. All right, now we, I guess, felt like the Celsius scale was not good enough, so we came up with a new scale called the Kelvin scale. Okay, now the Kelvin scale, the increments are the same. Okay, in other words, if the temperature goes up 1 degree Celsius, it would also go up 1 Kelvin. Okay, those increments, or like the steps, if you have two ladders sitting next to each other, their steps are the exact same height from each other. Okay, if one step is a foot, the other step is also a foot. That is not the case with Fahrenheit. Fahrenheit, the increments are much smaller. They're almost half of what Celsius is, a little bit more than half. Okay, so what's the difference between Kelvin and Celsius? The difference is not the length of the step. Instead, it is the starting point. Okay, 0 in Celsius is the freezing point of water. That's where you've got 0. In Kelvin, 0 is something called absolute zero. Absolute zero is the coldest temperature that it can possibly get anywhere in the universe. Okay, absolute zero is the point at which molecules are not vibrating at all. Okay, so there is no such thing as negative Kelvin. Kelvin starts at 0. Okay, or starts at absolute 0 and then counts up from there. Okay, so freezing point in Kelvin is 273.15, right? That is the freezing point in Kelvin. So that looks like a comma there, and I think it is a comma, but it should be all of these should be decimals, really. I don't know why they look like commas. It's probably somebody in England or something made it, and maybe they don't use decimals or something. I don't know. Regardless, the point at which water freezes on the Kelvin scale is 273.15. In the Celsius scale, it is 0. All right, so that gives you a good conversion factor. If you take Celsius and you add 273.15, you will get Kelvin. In fact, if you look at every one of these temperatures, if you took 100 and added 273.15, you would get Kelvin. So you know that Kelvin, on the Kelvin scale, water boils at 373.15. All right, and that is our formula. Not too difficult. I'm going to give you some problems to practice that, and that will do it for SI units. All right, so take some time to do the practice problems to the side, and then you're done for this, and then we'll go on to the next video, which is about something, a funny name. I always like these funny names, so I like to throw them in there. Something called dimensional analysis. It always makes it sound really challenging and crazy, but the reality is it's pretty straightforward. What it is it's about converting numbers between units and giving you a really simple and systematic way to do that. So join me then. Thanks.